Welcome to this lecture series on group theory. We are starting a new module which will be about subgroups. Previously we have looked at what is a group, we have looked at many examples of a group, and we have looked at the notion of the order of an element, and we also discussed some applications. So I'm not recalling these things because we have seen them many times. Let's directly start. So we want to introduce the definition or the idea of a subgroup, and let's motivate it via this example. We have the quaternion group. As a set, it is these symbols, but the multiplication can be captured via this diagram. We saw this before. So all the 8 elements have been labeled or marked inside circles, and how to transition from one to the other in this diagram determines how to multiply things here. So for example, if you multiply things on the right side by I, that is dictated by the red arrow. For example, if you take the symbol k bar and multiply that by I on the right side, you get j bar. So this arrow is just saying that j bar is equal to k bar times I, right? So following the red arrow means right multiplication by I. Following the blue arrow means right multiplication by j. Okay, but what about, you might ask, multiplication by k? How do I capture multiplication by k here? That's not seemingly not present in this diagram. But notice, if you start at the identity and you follow red and then blue, you get k. So we see that k is nothing but identity times I times j. When I say times, I mean the group operation. This, if you want, you can suppress it, write a star in place of it, or don't, I mean, to do whatever. I just mean the group multiplication. So yeah, so k is right multiplication by I applied to E, and then again right multiplication by j. So you land up at k. So k is, we see I times j. That's what we see, because identity times I is just I. This is k. Now suppose I wanted to multiply something on the right by k. Suppose I had this guy I bar and I wanted to multiply it on the right by k. What would I be doing? I would be doing this, which is same as I bar times I times j, which I might think like this. So that is applying the red arrow and then applying the blue arrow. So whenever you want to multiply something by k, you just follow the red and the blue arrow successively. So if I multiply I bar by k, what would I get? Follow the red and the blue. Where is the blue? Yeah, so you get here. So this thing, when multiplied on the right by k, gives that. Right, so all the information of the group is captured in this diagram. You can verify that for yourself. And here is what we want to note. Suppose I bring into the forefront this aspect or this part of the diagram. Everything else I have faded out. So here what's going on? Note that if you keep multiplying by the red arrows, you do not walk out of this region, right? Because you keep cycling around. If you multiplied by the blue arrow, then you would go out. But suppose you only multiplied by the red arrows, you would stay here. Which means that if you multiplied any of these guys with any of these guys, you would stay here. For example, suppose I multiplied this with that. But multiplying anything by that, or rather, sorry, let me trace back. Suppose I want to multiply this with that. Let's take that. Now multiplying anything on the right by this is as good as following the red arrow twice. That's the kind of thing we discussed here, right? Suppose you wanted to multiply anything by E bar on the right. I'm claiming that is same as follow the red arrow twice wherever you start. So suppose I wanted to multiply this by this element on the right, I would follow the arrow 2 times and I would land here. And why is that true? Well, what is E bar? E bar is I times I. Because you apply I and then you apply I. Multiply by I on the right, multiply by I on the right. Follow the red arrow 2 times, you get to E bar starting at the identity. And now if I wanted to multiply x by E bar, I'm just doing xi, and xi is follow the red arrow starting at x, and this is follow the red arrow starting here, which is same as saying follow the red arrow 2 times starting at x. So that's the kind of thing we said here, but I repeated it for emphasis. So here is what you can convince yourself, if all of this was not clear, that if you multiply any 2 things here, you stay here. You don't walk out. So this is closed under the binary operation of the group. Whatever that means, we will properly define it, but I'm sure you are getting the hint of it. Also, if you take the inverse of anything here, what is the inverse of I bar? That is I, right? So it is also closed under inverses. Basically, what we kind of see is that this itself is a group. If you remove from your view everything that has been grayed out, under the binary operation that was present on Q8, this guy still is a group. The binary operation restricted to this set is also a binary operation because you're never walking out of this set when you multiply two things here, any two things you like. So the binary operation on Q8 genuinely restricts to this set, and further, under that restriction, this happens to be a group that you can verify. There's a similar phenomena happening one more time in this group. This time I faded out other things. I faded out this guy, that guy, this guy, that guy. 4 things I faded out, but these things are in our view, and the same thing happens here also. If you multiply any two things here, any two things you like, you will stay here. You will not fall out of this set. And you can check that this thing is a group. These 4 things together form a group under the restricted binary operation. So this is the idea of a subgroup. A subset which is closed under the binary operation of the group. If it becomes a group in its own right, then it is called a subgroup. All this may be not very clear right now, but now we will formally define everything. So first we will define what is meant by closure under multiplication. Fix any set and star be a binary operation on the set S. So we are not talking about groups here, just any set with a binary operation on it. And suppose we have a subset of this set S. We say that A, this subset, is closed under star, the binary operation on S, if whenever you choose X and Y in A, you see that X star Y is also in A. So the terminology is self-explanatory. Right? The set A or the subset A of S is closed under the binary operation star, meaning you can keep applying the binary operation and you will stay within A if you start with 2 elements of A. Natural definition. And now we can talk about what is meant by a subgroup. So suppose we start with a group. G is a group and star is denoting its binary operation. Suppose we have a subset H of the group G. Then we say that H is a subgroup of G if, first of all, we want H to be closed under star. So philosophically, the idea is that H should borrow star from G and become a group in its own right. And for that to even make sense, first of all, we should have closure. What does that mean? It means that H is closed under star, which was defined above. This phrase has meaning because of this discussion. If you pick 2 elements in H and multiplied them, well, they are. If you pick 2 elements in H, they are also 2 elements in G, so you can multiply them via star. This just says that you will always remain here. Okay, and inheritance, this is the final thing. Inheritance means that this thing is a group. Since by closure, this thing is a set with a binary operation now, right? Well, when I write star here, strictly I should write star restricted to H cross H. Star was a function from G cross G to G, but because of this, you can think of star also as a function from H cross H to H. Notationally, we should qualify it with some horrible thing like this, but we don't do it. It's unnecessary burden. Okay, so I hope you understand what this means. Okay, so this thing is a group, is part of the definition of H being a subgroup. Natural, everything is very natural. We are not making any convoluted or controversial points. And before I proceed, this prefix sub is very common in mathematics. Since I'm assuming you know linear algebra, you've seen the notion of a subspace. We have a vector space, and then we have subsets of the vector space, which themselves can be thought of as vector spaces in their own right. This is exactly the same thing in the setting of groups, right? So it's not really a new concept to us in that sense. Okay, let's observe one small thing, that Just because something is closed under the binary operation doesn't ascertain that it will also have this inheritance. So for example, Z is a group, N is a subset of Z, which is also closed under the addition, which is closed under the binary operation of Z. But N is not a subgroup, meaning it is not a group if you restrict the plus. You know, this is a set with a binary operation, but this is not a group, right? You can easily prove that this is not a group. So this is required. You cannot just throw away this. But we will see that in some cases you can actually not write it and still it will be equivalent to what we said. We will look at them later in this lecture perhaps. Let's see. So now let's look at some examples. So this is a lousy example. This is a subset of this group R star. Recall what is R star? R star is R where you throw away the zero element, and R star is a group under standard multiplication of real numbers. So this is a group, this is a subset of it. Is it closed under multiplication under the usual, under the binary operation here? It is, because 1 times 1 is 1, 1 times minus 1 is minus 1, minus 1 times minus 1 is 1. So this is closed under the binary operation that is present in R star, and it is also a group when you restrict that binary operation to it. So this is an example of a subgroup. This is another example. Again, R star is a group that we just discussed, and this is a subset of R star. Clearly this is closed under usual multiplication. If you multiply two positive reals, you get a positive real. So the binary operation restricts to this guy, and this is also a group under that binary operation. So this is also an example of a subgroup of R star. So we saw two different subgroups of R star. One is R plus, meaning all the positive reals. So yeah, I should have explained this notation. This is just all the positive reals. Right? So fine, let's see more examples. So we have C star, which is, again, recall, C star is C, but you take out 0. And it is a group under the usual multiplication of complex numbers. And S1, recall, S1 is unit magnitude complex numbers. All those complex numbers which have unit magnitude. Let me write a C star there. Doesn't change anything, but still. And clearly this is a subset of C star. This is closed under the usual multiplication of C star, because multiplication of two unit magnitude complex numbers leads to a unit magnitude complex number. And you know that this is a group under that binary operation. We discussed this many times. Another subgroup. So this time we have this as our group with the composition of endomorphisms as your binary operation. This is a group, we know. The same group operation restricts to make this into a group. So SLV is of course a subset of GLV. What is SLV? SLV is those things in GLV with the determinant 1. What is GLV? GLV is all the invertible endomorphisms, invertible linear endomorphisms of the vector space V. Just recalling. So this is SLV, and clearly if you multiply two things here, or I mean by multiplication I mean composition, because the group multiplication here is composition. So this is closed under the group operation of this guy, we saw that, and this is also a group when you restrict the binary operation to this. So we anyway looked at this example earlier, so we know this. I'm just right now trying to point out that this is a subgroup of that. And this is another example which you can think about. If you have an inner product space, if V is an inner product space, you can talk about these guys. You can talk about these guys. These are just the orthogonal transformations, meaning inner product preserving transformations. And they are a chain of subgroups. This guy is a subgroup of GLV. This guy is a subgroup of OV. SOV is what? SOV, recall, is nothing but the determinant 1 inner product preserving maps. So SOV is nothing but OV intersection SLV. We saw all this. So fine, so this is one list of examples. We will look at many more examples in the course of this module and in the course of this lecture series. But for now, I think this is a decent introduction. Okay, let's proceed. Yeah, so any group has two trivial subgroups. So suppose we have a group G. If G is a group, then the entire subset, or I mean, what should I say? If you take G itself as a subset of G, that is of course a group or a subgroup of G. So G is a subgroup of G, and the identity element, when thought of as a set, the singleton set which contains only the identity of the group, is also a subgroup of G. It's just a matter of checking the definition. Clearly this is closed under the binary operation that is there in G, trivially. And clearly this is a group because this was a group to begin with, nothing to do there. This is also closed under the binary operation that was there in G. E times E is E. And this is a group in its own right. Yeah, after you restrict the binary operation to this, something that is so hard to do because it is such a complicated object, and you can observe that this becomes a group. So these are called trivial subgroups of the group G for trivial reasons. Transitivity. Suppose we have a group G, inside there is a subgroup H, and now H is a group in its own right. So for now, suppose our universe becomes H, and H says that I have a subgroup K inside of me. Now K is also a subset of the group G. So it's a natural question, is K a subgroup of G also? K is a subgroup of H is a subgroup of K, sorry, here I meant G, not K, this was a G. H is a subgroup of G, then K is a subgroup of G. So we are asserting that that is indeed true. Try to make sure that you understand the content of this theorem. When we say H is a subgroup of G, we mean that H is closed under the binary operation that was there in G, and H became a group when you restricted that binary operation to H. K is a subgroup of H means K is closed under the binary operation that was there in H, but that is the same binary operation that was there on G, just restricted. So in order to show that K is a subgroup of G, the first thing we needed to check was that if you restrict if you picked two elements in K and applied the binary operation of G on them, you will land in K again. And that is indeed true because of what we just said. So just verify that for yourself if that is not clear. And it's more or less a tautology that K is a subgroup of G after that, because we are saying that K is a group in its own right. When we said that K is a subgroup of H, we are saying that when you restrict the binary operation from H to K, you get a group. But the restriction of the binary operation of H to K is the same thing as restricting the binary operation of G to K. It's the same thing. So yeah, I'll leave you to check the details if it is not clear. So these two fundamental, very basic properties of subgroups are there, just like in linear algebra, subspace of a subspace is a subspace. Subgroup of a subgroup is a subgroup. That's how you can say it. And in linear algebra also, we have trivial subspaces. This is a trivial subspace and this is a trivial subspace of the vector space V. So just a parallel of linear algebra. Okay. Yeah, so now for some more natural questions. So we have a group G and within it we have a subgroup. Okay. Now, since it is a subgroup, therefore it's a group and hence has an identity element. So there is an identity element of it, we'll denote it by EH, E sub H. And there is an identity element of G, which we will denote by EG. The question is, are the two things same? It's not obvious. It's not immediately obvious. But the claim is that indeed they are the same. The identity of any subgroup is the same as the identity of the parent. It's not at all hard to prove. So consider this equation. Clearly this is true because EH is the identity of H. So let me draw or mark EH here. This equation was written with the point of view of H, right? H is a group, EH is its identity, so we will in particular have this to be true. But I can also think of this equation as written in G. That's completely fine because the binary operation on H and on G is exactly the same binary operation. It's just that on H we restricted it. That's all. It's the same binary operation. So this equation can be viewed in G also. Anyway, EH I can write as EH star G, EH star EG. So this equation I have written with G in mind. In the group G, think of EH as just some element. So this is of course true because X equals X times EG for all X in G, right? EG is the identity of G. So we have that. Now just look at these two things. These two things are equal. And you can think of that as an equation in the group G where EH times something is EH times EG. So by the cancellation property in the group G, we see that EH must be equal to EG. So let me just write down that step. So this implies in particular that EH times EH is EH times EG, which by the cancellation property gives us that EH equals EG. Make sure you understand all the subtleties that are there present in this argument. Not very much, I mean, there is not much subtlety, but definitionally there are some. When you write this equation, make sure how we arrived at it, right? You arrive at it by using the hypothesis that H is a subgroup of G. Star is the binary operation that was there in G, and that when restricted to H is a binary operation on H. So we can write this equation. Since H is a group, H is a group in its own right, and this was the identity element of H. So this is legitimate and so on and so on. So just make sure you follow all these steps. It's important. Okay, now suppose we have a group G and H is a subgroup of it just like before, and X is an element of H. Now we can do two things to X. We can forget about G and just restrict our attention to the group that H is and invert X inside H, right? So we will get some other element which is X inverse. But we can also think of X as an element of G and then take its inverse. We can potentially land at some other thing. But the lemma that we are going to prove is that no, it doesn't matter where you invert. So there is no ambiguity. The inversion doesn't need to look at which subgroup I am part of or this or that, nothing. Right? So again, first of all, the meaning of this statement must be clear, and then we are going to give a proof. Okay, so why is this true? We know by definition of the inverse of X in H that this is the case. This is the identity of H, but I'll just write E because by the previous lemma, the identity of G and the identity of H are the same. So I do not need to qualify this with a subscript. I do not need to write an H here. So we have this equation. This equation was written by considering X as an element of the group H. Now we have the same equation or similar equation when thinking of X as an element of the group G. So we can write this. Right? Forget about the subgroup H that there was. There is an element X in the group G, so we can of course write this. And yeah, so when my notation is a little off. What I should have written is this. It's X inverse sub H. X inverse and then sub H. That is how I intended to write it, but I was not careful. Right, so I hope you understand both these equations. And these give us that X star X inverse H is X star X inverse G. And by the cancellation property, cancel out the X, we get X inverse taken in H is X inverse taken in G. So that's very nice because now whenever we want to invert something in a subgroup, we do not need to qualify that inverse with some fact or some statement that we are taking the inverse in the subgroup H, not in the supergroup G or something. No, we are just taking its inverse. There is no ambiguity now. And here is one more thing. If H is a subgroup of G and X is an element of H, then the order of X in H is same as the order of X in G. So the content of this should be clear. X is an element of the group H, so it has some order when you just focus on the group H, but X is also an element of the group G. So there also you get a notion of order of X, but those two things coincide and I want you to prove it yourself. It's nothing. Just follow the definitions. Okay. Okay, so we will look at some ways to check if a given subset is a subgroup, right? So we have a group G, we have a subset of the group G. This is just a subset. Then this subset is a subgroup of G if and only if two things happen. First is closure. So this we already know. This is the closure property. Closure under the binary operation. I'll just say closure under multiplication. And the second is, well, before we get to the second, we just noticed in a few slides ago that this is insufficient to ascertain that H is a subgroup. The natural numbers sit inside integers and they are closed under the group operation. The multiplication is actually the usual addition. Okay. But N is not a subgroup of Z, right? N doesn't become a group in its own right. So we need something more than just this. And what is that? That it is also closed under inverses. I don't know why have I written this one more time, because it's already written over here anyway. So we are also insisting that H is closed under inverses. So whenever we are given a subset of the group G, it is a subgroup if and only if, first of all, it is closed under multiplication, and second, it is closed under inverses. Note that here when we say closed under inverses, there is no ambiguity like there was in the previous slide. H is not a subgroup yet. When we are checking these conditions, H is not a subgroup yet. So when we are talking about inverses, they are inverses in the group G. There is no meaning in the statement if we infer it or if we interpret it to mean that we are taking inverses in H. That has no meaning. We are checking if H is a subgroup. So this inverses means inverses in G. To make this very precise, what the statement is saying is that for all elements in the set H, H inverse is also in H. So here when I write H inverse, it is just the inverse in the group G, because we can't even talk about inverse in the set H anyway. So this is what we want to establish. Okay? And what do we need to do? We need to do two directions. First, if we assume that H is a subgroup of G, then we need to show that these two hold, and conversely. So first, assume H is a subgroup. Then by what we have discussed in the previous page, clearly, well, by definition, first of all, it is closed under the group operation. And this has been discussed in the previous slide. When you take the inverse of an element of H in G, that is same as the inverse of this element taken in H. H is a subgroup, so we can talk about the inverse of H in H. And we have already shown that those two things are the same things. Whether you take the inverse in G or you take the inverse in H, you'll always land on the same point. So closure under inverse is also shown. So let me just say dot dot dot. I have set it in words that you can fill up. The other direction is what I want to do, which is also trivial. So now assume 1 and 2 hold. Okay, so we want to show that H is a subgroup. H is a group in its own right. So we know that by this property, we can talk about H comma star, where star is the binary operation on G. And H comma star is a meaningful object in the sense that star restricted to H is a binary operation, thanks to 1. We want to show that it becomes a group. And what do we need to do? What do we need to do? We need to show that there exists an identity element in H, and everything has an inverse. So to show the existence of identity, associativity is given for free because the binary operation on G is associative. So when you restrict it to H, it will remain associative, right? So that I'm not arguing. So existence of identity is first thing that we should argue. Existence of identity. So let H be any element in the set H. And here maybe I should have said that this subset is a non-empty subset. Maybe I should have said that, but we are not here to develop the theory of the empty set. So fix any element in H, then by 2, this is in H, right? I just took the inverse of H in G because I anyway can't take the inverse of H in H. We are trying to ascertain that H is a group. Right now, we don't even know if H is a group, so When I write this, there is no ambiguity. So we know this, and now by 1, and hence by the closure under multiplication, we know that if we multiply H with H inverse, because both of them are elements of H, this is also in H. But what is this? What is H multiplied by H? Maybe I'll write a star just for emphasis. That is the identity of the group G. So the identity of the group G is there in H. Let me write a G here just for emphasis. So the identity of the group G has been shown to lie in H, and this will serve as the identity of H also. This is serving as the identity of a bigger, badder object. Clearly, it will also serve as the identity of this object because it lies in it. So that shows the existence of identity, and existence of inverse is an exercise now. It's almost done anyway. So that is an exercise. Okay, let's move on. So here we are saying, suppose G is a finite group and H is a subset of G, then H is a subgroup of G if and only if H is closed under multiplication. So when G is a finite group, you do not need to check the second condition at all. It is automatically satisfied is the question, is the statement. In fact, I don't think you need the finiteness of G, only the finiteness of H is probably what is needed. Let's see. In the course of the argument, we will see that. So here is a proof. We just want to show that H is closed under inverses. So let H be an element in the group H. We want to show, by the virtue of the previous lemma, so even before writing this, I should have said that if H is a subgroup of G, that is clearly there. We are assuming that H satisfies this, meaning H is closed under multiplication, and we want to show that H is a subgroup. So I hope that is clear to you. And now to show that H is a subgroup, all we need to verify is the second condition, because first condition is automatically, it is already there in the hypothesis. So that is what we are doing, and we want to show that H inverse is an H, and of course when I write H inverse, I mean the inverse of H in G, because I can't even talk about the inverse of little h and capital H right now. Okay, so we want to do this, but here is the interesting idea, or something. So consider the sequence H, H square, H cube, and so on. All of these things lie in H. This was in H was closed under multiplication, so this is in H. By the same reasoning, this is in H, and we have a sequence in H. But since G is finite, H is also finite, so yeah, we only need the finiteness of H. So let G be a group and H be a finite subset. Okay, we need a weaker hypothesis. So since this is a sequence lying in the set H, but H is finite, so there should be some repetition here. If there was no repetition here, then H would become infinite. So consider the sequence, or note that this is a sequence in H, is a sequence of elements of H. But since H is finite, we know, or we deduce, that H to the power m should be equal to H to the power n for some distinct m and n, which I will write like this. One of them has to be bigger, so I will write like this. And hence, by this equation, we get that E is equal to H to the power n minus m. This E is the identity of the group G. This equation immediately leads to that equation. This is written in the group G. But this guy is there in the set H. This is just H multiplied with self some number of times. Since we have n is strictly larger than m, this is H times H times H so many times. And hence this lies in the set H, because H is closed under multiplication. And hence the identity of the group G lies inside the set H. Right? So fine, so that is very nice. But by this we also see that Eg is equal to h times h n minus m minus 1, right? So what we really wanted to do was show that the inverse of h is in h, but by this equation, the inverse of h is this guy, right? Inverse of h is this guy, and yeah, so this thing could be 0. That is one case that we need to deal with. If this is positive, this is either 0 or positive. If this is a positive integer, then this guy is an element of h. And hence we are done, because by this equation that we have, this equation shows that this guy is the inverse of h. Okay, so far what we have justified is that this is the inverse of h in the group G. So there are two possibilities. Either this is positive or it is 0. It cannot be negative because of this inequality. Either this is positive or 0. If this is 0, well then this becomes the identity element, and hence h inverse is the identity element, and hence h is the identity element. So if this is 0, then the thing was anyway trivial. Because if you started with the identity element of the group G, what is the inverse of the identity element? The element itself. So you will land, you will get the same element back, which was already assumed to be in the set H. So there was nothing to do there. Hence, the adverse case is when this is positive, but there, by the closure, by the assumption that H is closed under multiplication, this is an element of H, and hence this is an element of H, and that's it. So again, I don't want to write all of that unnecessarily. Waste time. So make sure you follow everything. Okay, these are very useful criteria. And I want to finish with this bonus example of a subgroup of the permutation groups. So for this, I will assume that you know about graphs. So by graphs, I do not mean things like this, plots of functions. No. A graph is basically a set of points, let's say finitely many points, and some of them are joined with edges. That is up to you entirely how you want to join them with edges, no restriction. It's just that we are not assuming that there are loops. You cannot join a vertex with itself via an edge. And when we say edge, we do not necessarily mean straight edge. It is just some abstract edge. The formal definition of a graph you can check out, or you can skip this section if you do not know what is a graph. So I'm assuming you know what is a graph. V is the set of all, set of the first n integers. And suppose we have a graph on the vertex set V. So E is the set of edges. Formally, it is a collection of two element subsets of V. This is just an example of a graph. This is called the Peterson graph. So an automorphism of gamma is a map, is a bijective map, phi going from vertices to vertices, such that if you apply phi to an edge, you get an edge, such that phi of u comma phi of v is an edge whenever u comma v is an edge. That's the definition of an automorphism. Okay, and you can check. So here is an exercise if you're interested in this example. So let aut gamma be the set of all the automorphisms, all bijections from V to V, such that phi is an automorphism of gamma. Show that this is a subgroup. Aut gamma is a subgroup of the symmetric group on, or the permutation group on V. Recall, this notation stands for the set of all bijections from V to V, which is a group under composition, and we have created a subset of it, right? Clearly this is a subset of it. Exercise is to show that this is a subgroup of this. All you need to do is check that it is closed under the group operation. It is already a finite set, so you do not need to check for inverses. Just check that it is closed under compositions. Composition of two automorphisms is again an automorphism is all that you need to check. And that would give a very nice subgroup of the permutation groups. You can create very interesting subgroups, right? Depending on how the graph structure that you start with looks like, this can be very complicated to understand. So that's very nice. And this is a general philosophy here. Graphs are not very important. Any mathematical object admits or begs for its group of symmetries. Here the object is a graph. So all we are doing is collecting all the symmetries of a graph. This word is basically a synonym of symmetry, right? So yeah. Okay. So this is all that I wanted to say. As usual, like, comment, share, subscribe, and I will see you next time.